Modern-day power systems are moving away from traditional designs which consisted of reliable generation sources, connected through transmission and distribution networks. A new topology comprised of embedded generators and variable renewable sources is emerging as we target lower emission levels. This transition has given rise to challenges, particularly for engineers responsible for the secure operation of their networks and the reliability of the schemes protecting them. The increased penetration of inverter-based generation has seen fault currents change in both magnitude and nature. In addition, source-to-line impedance ratios have increased, and negative and zero-phase sequence contributions have altered. Compounding these changes, increased levels of embedded generation have given rise to varying levels of bidirectional power flows which must now be accommodated. Traditional protection design and coordination approaches lack the efficiencies and sophistication required to address these challenges. They consider pair-wise coordination of like relay elements on specific grading paths. The investigation of multiple system configurations, or even various fault types and locations, is time-consuming and inefficient. These traditional approaches also lack the required sophistication. Investigations are limited to the response of main relay elements at fault inception, based on generic relay models with interpreted settings. Supervisory elements and internal logic functions are assumed to be satisfied, and coordination is simply expected to be maintained throughout the entire fault clearing cycle. Given the complexity of the modern relays and protection schemes, and the different network topologies that can present throughout the fault clearing cycles on today's complex power systems, these assumptions can no longer be relied upon. Protection security assessments address these traditional shortcomings. Accurate network models capture detailed bus configurations and plant item locations for the correct positioning of measurement transducers and summation of inputs, and also allow for the identification and consideration of blind spots. Advanced steady-state representations of inverter-based generators, and their control systems are included to determine realistic current contributions from these devices. Protection performance is analyzed using a time-stepped event simulation that examines the time interval between the fastest protection responsible for clearing the fault and all backup operations. These coordination time intervals are considered at each stage of the fault clearing cycle, not simply at fault inception, and operating times are integrals of the responses across the changing conditions. Using this approach, the assessment considers all protection elements in the study area that respond to the disturbance, regardless of type and location. The analysis is based on relay-specific models that capture the actual comparator equations, supervision elements and internal logic. The settings are applied using the relay taps implemented by the manufacturers and can be downloaded from relays. All relay types including distance, differential, and elements using current, voltage and phase sequence component are supported. The protection models also capture the power utilities protection scheme logic. Pilot-assisted schemes, blocking functions and remedial action systems can all be considered. The advanced time-stepped analysis is exercised on the comprehensive network and protection models for a range of system operating configurations and credible failure scenarios. Plant outages and protection and communication system failures are investigated under a range of fault conditions. Various fault types and locations across large areas of the network are considered to identify protection performance issues. Powerful data management and visualization tools allow slicing, dicing and consolidation of the comprehensive assessment output. Problematic network areas and operating contingencies, together with underperforming protection installations and inadequate relay models, can be identified. The underlying studies identifying these inadequacies can be initiated from the assessment outputs for a more detailed investigation of the performance issues. Protection security assessments allow regular comprehensive reviews of wide area protection systems to be undertaken efficiently. They identify sensitivity issues and miscoordinations, delayed fault clearances, inadequate setting design criteria, and limitations of relay models and technologies. These capabilities address the challenges posed by networks with constant changing topologies and supply configurations, and fault currents that vary in magnitude, sequence composition and transient behavior. Engineers now have the means to ensure protection system dependability, and network operating security is maintained on today's complex power systems.